Statics is a branch of engineering mechanics that focuses on the study of bodies in equilibrium. At its core, statics relies on Newton's laws, which provide the foundation for analyzing and understanding how forces act on physical systems. Newton's laws are fundamental principles that describe the relationship between a body and the forces acting on it. They are the cornerstone of classical mechanics. The first law, or the law of inertia, states that if the resultant force on a body is zero, the body remains at rest or continues in motion without a change in direction or speed. This can be expressed as sum of F equals zero. The second law, or the law of acceleration, states that a body will experience an acceleration proportional to the net force acting on it. This is described by the following equation. The third law is known as the action-reaction law. It states that for every action, there is an equal and opposite reaction. This can be expressed as the following. These laws are used extensively in statics to analyze bodies and structures to determine both external and internal forces. To determine the external forces acting on a system, static analysis uses free body diagrams. A free body diagram isolates an object from its surroundings to illustrate all external forces acting upon it. Consider a box placed on a surface being pulled. The free body diagram for this scenario includes a normal force, which is the perpendicular force exerted by the surface on the box. A tension force, this is pulling force exerted by the cord. A friction force, which is the resistive force between the box on the surface and the weight of the body, which is the gravitational force acting on the box. These forces are represented in the free body diagram, and by assuming equilibrium in all directions and then applying Newton's laws, the sum of forces can be set to zero to solve for any unknowns. In many real-world scenarios, forces are not concentrated at a single point, but distributed over a length, area, or volume. These are known as distributed forces. The resultant force magnitude and location can be calculated for a distributed load. For example, the location of the resultant force for a uniform distributed load is the centroid of the load, which, for a uniform load, is at the midpoint of the distribution. Additionally, the area under the distributed load can be calculated for the magnitude of this resultant force. Static plays an important role in determining internal forces within structures like trusses and beams. These internal forces are crucial for evaluating the structural integrity of a system. Understanding these forces helps engineers design structures that can safely withstand various loads. The most common internal forces are a normal force, which is a force that acts perpendicular to the cross-sectional area of a structural member. It can be either tensile or compressive. The second common internal force is a shear force. The shear force acts parallel to the cross-sectional area of a member, causing the material to slide along the plane of the force. Third, bending moments. The bending moment is a measure of the rotational effect produced by forces acting at a distance from a point or axis. It causes the member to bend, generate tensile and compressive stresses within the material. In statics, following consistent sign convention is crucial in summing forces and moments to ensure accurate calculations. Let's look at an example. For a beam fixed at one end with force F applied at an angle theta at the other end, internal forces and moments can be analyzed by making an imaginary cut at any section along the beam. Then, by applying equilibrium conditions with the correct sign convention, we can use the following equations to determine all internal forces. These equations help determine the normal force, shear force, and moment at a cut section. The normal force ensures that the beam resists axial loads, the shear force resists sliding, and the bending moment resists bending. Understanding internal forces is crucial, but it's equally important to recognize how structures interact with their supports. The type of end constraints, such as fixed, bend, or roller supports, greatly influence the reaction forces and moments within a system. In 2D statics, we typically consider 3 reaction components, 2 force components, and 1 moment component. Depending on the type of support, different reaction occurs. For instance, a fixed end resists both translation and rotation, leading to reaction forces in both directions and a moment. On the other hand, bend ends resist translation but allow rotation, resulting in reaction forces but no moment. Additionally, roller supports resist translation perpendicular to the surface but allows movement along the surface and rotation, leading to a single reaction force. When we move into 3D, the complexity increases as more components are considered. In 3D, we deal with 6 reaction components, 3 force components, and 3 moment components. Incorporating these additional components ensures that the structure's response to all possible loadings is fully understood and can be safely designed. And this is it. This was a quick summary of statics. If you liked this video, don't forget to like, subscribe, and hit the bell icon for more similar tutorials. Thanks for watching.